Although Einstein's theory of special relativity may appear somewhat strange, it has actually been experimentally verified. And one of the main ways that we've looked at doing that is by studying small subatomic particles called muons, and we'll meet them more in the particles units later on. But in the lab, so in a stationary reference frame, muons are found to have a half-life of 1.56 microseconds. Now, muons are formed in the upper atmosphere when cosmic rays strike the upper atmosphere, and that's about 60 kilometres above the surface of the Earth. And they can travel at speeds of 99.96 times the speed of light. So their speed, the time they would take to cover those 60 kilometres then can be calculated to 60 times 10 to the 3 divided by 3 times 10 to the power 8. And 99.96 is basically roughly 3 times 10 to the power 8. And that comes out to be about 0.2 milliseconds. Now that is a lot longer than the half-life of 1.56 microseconds. So there are more than 100 half-lives in that. So they should be well decayed by the time to get to the Earth. So we shouldn't observe muons naturally being produced at the surface of the Earth. However, we can actually quite easily detect muons on the surface of the Earth. Why is that? Well, the answer to that is to do with special relativity. The muons are moving in a reference frame compared to us. So the experience, when we're observing them, we see their time as being dilated. And we find that their half-life is about 55 microseconds, which is not quite the 0.2 milliseconds, but is a lot closer. So if we considered a large batch of these muons being produced at the same time as happens when the cosmic ray strikes the upper atmosphere, and considered that they've got a half-life, then remember that doesn't mean they'll all disappear within that half-life. Some of them will survive to reach the surface of the Earth. So the fact that we can easily detect muons on the surface of the Earth is experimental verification of Einstein's theory of special relativity.